So now let's take a look at example number 2 and continue to try to use these different calculator commands to our advantage. Let's see what we have here. A company claims that their light bulbs have a mean lifetime of 750 hours and a standard deviation of 10.6. Assume the lifetimes have a normal distribution. Okay, but again, before I even go to part A, I'm going to follow the progression that we already had seen on the formula sheet, which stated that first I better be able to write down and express what the random variable x actually stands for. So I'll say here, how about we let x represent the length, or you could say, maybe instead of the length, I'll say the lifetime of a light bulb. Now, the way that I know that this is what I want x to represent is because I can already see that when I have my mean and my standard deviation, they're actually talking about the lifetime of light bulbs. So I'm going to go ahead and let my random variable represent the same thing. Then I can say that x, which again represents the lifetime of a light bulb, has a normal distribution. And I can also state the important parameters. So I can state that it's got a normal distribution where the mean is going to be 750 hours and the standard deviation, that's 10.6 hours. So again, I'm just progressing right down that formula sheet. Well, now let's take a look at part A to see how we can answer some questions. What proportion or what percentage of light bulbs have a lifetime that is less than 725 hours? Well, this again should hopefully be a fairly easy question by this point, because I know that I can just draw out a number line, sketch out a nice normal distribution. This one here is going to have standard deviation of 10.6. And I'm interested in getting a proportion or a probability that is less than 725 hours. So 725 would be right here on the number line, somewhere around there at least. And I'm going to go ahead and shade less than that. So what calculator command can I use? Well, I would use a normal CDF. I'm calculating a probability, so I'm going to use this probability notation. The probability that I get an x that is less than 725 can be found by setting up my normal CDF. And then, remember, I'm going to have to do my left side and my right side. So I'm going to have a negative 1e99 up to a 725 with a 750 and a 10.6. If I go to my calculator, I can type all this stuff in and get to a final answer. Now, I'm not going to go ahead and do that right now, but I'll just go ahead and write down the result that I would get if I had typed this in. The result should be 0.0092. Notice that's equivalent to stating that over here in the picture again, my amount of shaded space is equal to exactly 0.0092, or 0.92%. Well then, notice that something like part B becomes a very, very simple question to ask. Would it be unusual to actually go and grab a light bulb and find out that it is one of these light bulbs that lasts less than 725 hours? Would it be unusual to say grab a bulb off the shelf and actually have it last less than 725 hours? Well, remember that earlier in this semester we talked about the idea that in order for an event to be unusual, we defined that as an event that had a probability of occurring that was under 5%. So, is the chances of getting this type of light bulb under 5%? Absolutely. It's not even at 1% yet. So we can say absolutely yes, it would be unusual. Again, here we know that that's the case because the probability of such a bulb being found or being selected is what, 0.92%, which is very, very, very small. It's definitely under my 5% mark. Okay, well, now let's take a look at part C. About how many light bulbs out of 100,000 would you expect to have lifetimes of less than 725 hours. Well, this is kind of interesting. Okay, so we know that the chances of getting one of these types of light bulbs that lasts under 725, that's only about 0.92% of the time you find such a bulb, or 0.92% of all bulbs meet this description. So actually what we see down here is we have a very, very simple sort of a setup. We have 100,000 bulbs total, and we know that only this percentage of them, roughly speaking, should actually be light bulbs that meet this criteria of lasting less than 725 hours. So we could just easily go ahead and compute this by just saying, let's take 100,000, let's multiply that by our 0.0092. That's the percentage of bulbs that we expect to get. And then I can crunch out a value on the other side. Now, fortunately, this value here is actually really easy to crunch out. You can confirm for yourself that you do end up with 920. Now, I'm really quickly here just going to highlight, again, what each of these different values here actually meant. So this here was the total number of bulbs that we were looking at. This was the percentage of bulbs that we wanted, right? And so then this ends up being the total bulbs that we get. So notice that here I really just have some sort of like a formula set up with kind of 3 individual different values. And if I know any 2 of the values, I can easily solve for one of the others. Here it was just the case that we had the first 2 values. But if I instead change the question to say, hey, I have 100,000 light bulbs, and I want to end up with a total number of light bulbs that is, say, 436, then what percentage of the light bulbs do I want? Well, that's like super easy to find. I can just do some algebraic manipulations to get to where I want to be. So here we can definitely see, though, that our final answer is this 920 light bulbs. A very, very simple and straightforward question here. It doesn't really actually require any fancy calculator commands.